Okay, we're in the last video we were looking at differential equations. What we're going to be looking at today are something called slope fields. And slope fields are a helpful way for us to visualize a differential equation. So let's think about um, the idea of y prime equals y. Well, what that means is for any value of y, I know its derivative. So when if we think about a chart of y and the derivative, when y is 0, the derivative is 0. So notice everywhere here, when y is 0, we have a horizontal line representing little dash line, meaning at that point it has a slope of 0. When y equals 1, the derivative is 1. So up here at y equals 1, we have all these little small tangent lines with slopes of 1. And when y equals 2, the slope equals 2. So if we go up to y equals 2, now the slope is getting steeper. And the slope field, it's kind of like a magnetic field if you've done any work with magnetism. But the idea of the slope field is that there are an infinite number of solutions, just like there are an infinite number of solutions to this differential equation. But if I were to give you some point, if I were to say like you are at this point, you're at the point 0, 1, um, a graphical solution to this differential equation is just to follow the slope field. So we're following all those little lines. So this shows me a graph of the solution to this first order differential equation, provided that I go through the point 0, 1. Well, what if I went through this point here? So let's think about that. So we're at this point, and I'm just following the slope field down and following the slope field across. So here's an example of a slope field. You're going to be drawing some in a second, but for now, it's given to you. And just to be clear on how that happens, if we think about x points and y points and our corresponding derivative, when x equals 0 and y equals 0, our derivative is 0. So we see that there. When x equals 1 and y equals 0, my derivative would be 1. So x equals 1, y equals 0, we see a slope of 1. And when x equals 3, for example, y equals 2, we've got a slope of 5, and so we see this slope of 5. So it says sketch the curve through the point 0, 1. Well, that would be this curve right here, 0, 1, and we're just going to follow the curve. So this is my solution. This curve is the solution to this differential equation at that point. Now, we don't have an equation. All I have is a graphical representation. And in the next class, in the next video, we'll look at how to get this equation. But for now, we're just getting graphical representations. So one more, the solution through -2, 0. Well, that's here. And we get a pretty interesting graph. Looks something like that. Well, what if they don't give you the slope field? And speaking of slope field, there's a program that you're going to program into your calculator if you have an 83 or an 84. And I'll show you that at the end of the lesson. Um, so for now, we won't do that part. But it says consider the differential equation on the grid, sketch a slope field for the given differential equation at the 25 points indicated. All right, well, this will take a little bit of time. So at this point, y equals 0. So when y equals 0, my slope is 1 minus 0 is 1. So for all of these points, y equals 0, so it has a slope of 1. And then when y equals -1, 1 minus minus 1, we'd have a slope of 2. So I'm trying to get a slope of 2. And when y equals 1, 1 minus 1, we get a slope of 0. And when y equals -1, sorry, when y equals 2, we'd have a slope of -1. And when y equals 3, we'd have a slope of negative 2. So this is my slope field. And now it wants us to sketch the solution curve that goes to the point negative 1, 3. So that's negative 1, 3. So that's going to look something like, oops, like that. And since the slopes here are all 0, there's a horizontal asymptote, so it'll never cross that. Okay, let's do another one like that. It says, given the implicitly defined function, show that dy dx equals x over y. Well, now we're working backwards. So if we go, let's see, take the derivative, so we get 2x minus 2y dy dx equals 0, and we get that dy dx, solving it, equals positive x over y. Okay, well, what is that going to look like? It asks to use the slope field program, but I don't want to use the program. I want to get a sense of what this looks like, just sketching it quickly by hand. Okay, so if I fill in a couple of these points, um, when y is 0, it's going to be undefined. So when y is 0, we're going to have a vertical line. And when x equals 0, we're going to have a horizontal line. Let me just draw these in a little bit. Okay, and what about when x is 1 and y is 1, we're going to have a slope of 1. When x is 1 and y is 2, slope of 1/2. When x is 2 and y is 1, slope of 2. 2 and 2, slope of 1. Let's see. 0.31, it's going to be 3 and 3, 2, 3/2. And at 3, negative 1, it's going to be a slope of negative 3. And at 2, negative 1, it's going to be a slope of negative 2. And at 1, negative 1, slope of negative 1. And if I fill in the rest of these, so let's see, negative 1, 1, and 1/2. And what we see here, sorry, that last one should be a positive slope because it's negative 3, negative 1. So we're talking about a slope of positive 3. And here we're at a 3, negative 3, 1. So it's a slope of negative 3. And now negative 3/2. So the idea is, if I were to put a point down like right here, if I was to be at this point, the solution is going to be something that looks like that, which is a hyperbola. Because if I put my point there, we get a graph that looks like that, and we know because of our study of conics that is a hyperbola right there. And then we have just to go on to our hyperbola, we've got these lines. Okay. All right, so let's do one more filling in the differential equation. So just working through this kind of quickly. Uh, at 0, 0, it's got a slope of 0. Let's keep y 0, so when x is 1, slope of 1, x is 2, slope of 2, -1, and -2. Now let's go up, y equals 1, so at x equals 0, it's going to be -1. When x equals 1, 0. When x equals 2, it's going to be 1. -1 is -2, -3, sorry, -2 is -3. And now let's go up to y equals 2. So here you're going to have a slope of -2, slope of -1, slope of 0, slope of -3, slope of -4. Those are kind of hard to differentiate between the two. So now let's drop down to -1. So when x is 0, we've got a slope of 2. When x is 1, slope of 3. When x is 1, you have a slope of 2. When x is Let's say that again. When x is 0, we've got a slope of 1. When x equals 1, we have a slope of 2. When x equals 2, we have a slope of 3. When x equals -1, slope of 0. When x equals -2, slope of -1. And let's finish off with this last bit. Um, y equals -2. Here's a slope of -2, -3, -4, -1, and 0. So now it says find an equation for the straight line solution that passes through the point 1, comma 0. So 1, comma 0 is this point right here. And we notice that um, these are all just slopes of 1. So that equation would be y equals x minus 1. And I realized that on this bottom line, I made a couple mistakes. Uh, let's redo those. When y equals -2, this should have been a slope of 2, and this should have been a slope of 1, and this should have been a slope of 0. Yeah, that's better. So this green line was my a straight line solution to this differential equation going through the point 1, 0. And because of algebra and graphically, I can see that the equation for that is y equals x minus 1, because the slope is 1 for everything along this line. All right, so now let's think about how, can we match a function, a differential equation, to its graph? Well, um, let's start off with this easiest one to think about. I think is y prime equals sine of x. So we know that that has to be d because that's the only one that's looking trigonometric. And then if we look over, let's look at this first one. So y prime equals x, which means that as we increase my y's, as I just change y, the derivative shouldn't change. So provided that we fix x, my derivatives here don't change. And we can see that the slope, as I fix an x and go up, my tangent lines are all the same. And that's because for this particular graph, the derivative only changes when x changes. And we can see that graphically. So now we need to fill in these two. So let's look at this one. there's no x in it, so my derivative is only going to change when y changes. Using the same sort of reasoning as I go across and I keep y the same. So if I only change x, notice that the derivative doesn't change. So if I only change x here, the slope field stays constant. So therefore we know that this one goes to here, which leaves a and 4 as a solution. Okay, so let's just finish looking here. This is your program, and this is only for the 83 and the 84. So if you have an 83 and an 84, what I'd like you to do is program this into your calculator, and you should do that. The TI Nspire and I think the 89 have a slope field function already built into them, and you can, if you have an Nspire or an 89, just look online and see how to do that with your calculator. Otherwise, for an 83 and an 84, take the time to create this program, and if you need help, get some help with it. Uh, create this program, because what this program will do is it will generate slope fields for you, so you don't have to go through and do all those little draw all these tiny tangent lines. Okay, so that's it. That was drawing slope fields, and the whole point of slope fields is it helps us visualize the solution to a differential equation.